When deriving a certain set of equations, we normally use this format, right? But when you're talking about questions, okay, when you're applying all these things, okay, we're applying all these formulas, you can straight away jump into applying the formulas. Okay, so it's just like what does the question say? So if the question gives us whatever thing, so what are the given formulas that I can use in order to find our stuffs? So it's like a game. So you're trying to find your variables. Okay, you have certain things, and you're trying to use different formulas given to actually trying to derive a certain set of stuff. So without further ado, let's start. So I have a counter rotating eccentric weight exciter. If you remember last lesson we only have one. Okay, now in this case we have two, and it's used to determine the vibration of the structure weighing 1780 Newton, and it's rotating at a 900 revolution per minute, and then to be at the top, the structure was moving upward through its static equilibrium position. So we can understand that it is moving in one direction only. Okay, and the corresponding amplitude was 21.5 millimeter. Okay, so the amplitude itself is 21.5. So if the unbalance of each wheel of the exciter is, so these are the wheels, it's 45.9 kg mm, determine the natural frequency of the structure. Okay, so let us write it down. What are the stuffs that are given, so we can actually do it. So the first thing we are given is actually the weight. So we know that the weight is 1780 Newton, because what we are dealing with is always mass. Okay, so we have to change to mass. So we divide it by 9.81, which is the gravity. We have 181.45 kg. And then the second thing we are given is actually the angular velocity. They are turning, okay, the speed. So it's actually 900 revolution per minute. So one revolution, um, so what it means by 900 revolution. So in 1 minute, okay, in 1 minute you spin 900 times. Okay, you spin 900 times. One time, two times, three times. Okay. So in 1 minute you spin 900 times. So this is one key concept I want to make known, is that when you talk about revolution per minute, you can straight away change to omega, radian per second. So that it is the frequency. Okay. And in other words, revolution per minute is like how many frequency do you spin at this. So you have this point over here. So the first, also you spin one time, the second time, third time, fourth time. So how much time you reach this point, right? So it's the amount of frequency you reach this point in that sense. So how do you set up an equation? So you know the frequency is radian per second. So therefore you multiply 2 pi over 60. So what is this meaning? So revolution itself, it's one revolution, it's 2 pi, right? One revolution is 2 pi, and then 1 minute is 60. So you're just simply changing the units itself within it. So you're just trying to give it some units that correspond to radian per second, right? So therefore we multiply 900 times 2 pi over 60. So you have this value over here, the radian per second. Okay. And the next thing is amplitude was 1.5 millimeter. Okay. So the amplitude where it moves, when you have, so this is the position. So the amplitude itself is 2.15 times 10 to the nearly 4 meter, right? It's very small. So we're talking about vibration. The amplitude itself is actually quite small. Okay. So we're just talking about some millimeter, that's all that, yeah. So this is all we are given. Nonetheless, we also given the weight of the wheel, okay, the unbalance with the kg per kg mm. So we are given this thing saying that this is the mass multiplied by the how do I say it? The distance, I would say, right? So in other words, if you remember last video we talked about F naught is equals to me w square, right? So the mass multiplied by the eccentricity of the movement, of the motion, right? So itself by itself, this describes that. Okay, this describes M and E. Okay, so we are lacking the omega square. Okay, so if you take a look, so we are talking about ME because it's mm and kg, you know. So we are lacking with the omega square in order to have a certain force. Okay, so these are all the given stuffs. Okay, and then so so how does this what are this how does this information help us? Okay, so by far the datasheet itself we are given all these formulas. So I've cut and paste all the stuff that we need. Okay, so these are all the formulas. So how can we use this formula to apply? We have weight, we have part of the mass. So we have the part of the equation, we have the part of some equations, we have the omega, the frequency of the system. So do we have any frequency of the system? As you can see, there's no always in terms of natural frequency, right? Everything is natural frequency. And then the amplitude itself, you have x, right? So nonetheless, this is xm. You remember last video we talking about the trying to sub in, right? So this is actually mx. Okay. So it's a little. So you can really see that we are lacking a lot of stuff. Okay. Our given parameters can't help us to solve anything. Okay. But one piece of information is very important, which is this, right? Our balance of the exciter. So this piece of information, as you can see, is very important right now. It holds the key to all these things. So how do we use this, right? But nonetheless, let me introduce you to the system itself. So previously we talked about the first system. We talked about how it actually moves, right? Hold on. We talk about it is spinning in this manner, right? So in this case, okay, nonetheless I may be wrong, but in this case we have two of this shaft. Okay, there are also two of this shaft. So what does it do is that you have this system over here, this shaft turning. So there will be this shaft turning over here, right? While the rest of the shaft, while the other shaft that is shown in the diagram above, over here, where is it? Okay, yeah. So so let's say this one is your operating shaft. In order to prevent it to vibrate, you eventually want another shaft to move in a counterclockwise, so you will not vibrate that much. Try to have the same revolution. So in this case, you have less vibration. Nonetheless, yeah, you see. So this method will actually prevent certain damages to the damper itself also. So yeah. So let's go back to this one, right? So we talk about the wheel of the exciter is 45.9 kg kg mm, and knowing the equation that F naught is equals to this one, so we can straight away find our force. Okay, in this case, so hold on. So as said, this equation doesn't help us to resolve any given parameters, so we cannot sub anything. So therefore, we use our last parameter, the 45.9 kgmm. This is the out of balance force. Okay, so this force, so typically the force that we are talking about is always out of balance because it's always moving out of balance. Okay, it's moving here and there, up and down. Okay, so this is out of balance, and therefore you know that previously F naught. Okay, this is from our previous lesson. That F naught is equals to METW square. So this is something that you have to tap on your prior knowledge. You are not given in your equation itself. It's pretty tough. So let's do it, right? So since you know this equation in your heart already, so you know that this is kgm meter. So you can see that this is kgmm. So what we are lacking is actually radian second per second square. I mean radian square per second square. So what we do is actually we have our omega, right? Our angular velocity over here, which is this dude over here. So what you can do is actually to square it and then multiply it inside. But before that, we need to actually change this to meter, right? So we have to divide by 1000, right? So let's hold on a while. So actually, just now we talked about 49.5, right? Now it's actually 45 point. Just now we talked about it's 49.5, okay? I write wrongly, it should be 45.9 now, okay? So this is just a careless mistake, but nonetheless, let's continue. So we change kgmm to kgm by simply dividing by 1000, right? Because mm to meter, I think you already know. So, um, in another form, is you can actually times 10 to negative 3, so is all right. So it's kg meter. And then we know that radian per second is equals to 4.248, which is shown over here where I calculated. Radian square per second square is equals to this thing square, right? So with this set, we can actually submit into our equation 1. So I just put this in terms of equation 1. So we have m, we have e, we have omega square. So finally we have some equation that we can have full values, So we have 47.72 Newton. Okay. So these are all the initial parameters. Okay. So far what I'm talking is only dealing with the initial parameters. Okay, why we are going such a big chunk of time is because we realize that there are certain stuffs that we cannot sub into here, right? So we need to derive what we have, what we need, okay, what we have, and trying to see what we can do with this thing. Okay, so for next video we'll start to explain how we use this this understanding to help us solve for the rest. Right. So I shall see you in the next video.